welcome to the Space Policy Show. I'm Colleen Stover. This is our last show of the year, but don't forget you can browse all the shows at csps.aerospace.org while we take our little break, right? So today we're going to talk about exploration beyond JWST, James Webb Space Telescope. It's episode 111. Can you believe it? We've got two aerospace folks on the line. Dave Eccles is the general manager of the National Space Systems Engineering Division. He's also deputy director of the Center for Space Policy and Strategy. Thanks, Dave, for coming.
Thank you. It's good to be here.
Yep. We've also got Dr. Kenneth Harris with Aerospace. He is a senior project engineer, and he's in the Systems Integration and Protection Division. Kenneth, thanks for being here.
Pleasure to be here. Thanks for having me.
Yeah. So I'm going to ask you guys to introduce yourselves just briefly, and I'll start with you, Kenneth. You've got a particular background that I was very interested in having on the show. So why did I invite you here? What does your background speak to?
Sure thing. My name is Kenny Harris. I've been working with NASA specifically for about 15 years now. Started as an intern. I had a great opportunity in high school and throughout my undergraduate and graduate degrees. I'm a mechanical engineer by trade and by background. So I did a lot of the integration work on the James Webb Space Telescope. And we'll get into that a little bit here today. Very, very proud of the project, really excited to talk about it. Currently for Aerospace, I work on program protection strategies for the Artemis program and a handful of other projects for NASA, DOD, and the NRO. So pleasure to be here today.
Great, thank you. Now, Dave, you kind of grew up more on the defense side than the civil. So give us a couple sentences. Why do you want to be here today? Why did I ask you on?
Well, I think it's because deep space exploration and finding out what's out there has always been something that has sort of lit my imagination. I grew up in Southern California, not far from the Jet Propulsion Laboratory. And while I've been in aerospace, I've been able to work on a lot of different projects, probably about 50 or 60 different programs in the last 40 years. One of the most exciting was when we were asked to do an independent review of the Cassini program from top to bottom 1 year before launch. And just learning about the complexities associated with creating such a complex system. And of course, JWST is probably about the most complex systems engineering system that we've ever put in space. Just fascinated by the way these systems work, but even more fascinated by what they can tell us. And just from when I was young, being close to JPL and following that, that's why I wanted to be on the show today. Yeah, I've worked on a lot of defense programs, but defense programs aren't looking out, they're looking in. And looking out is just a very exciting prospect for me. That's why I'm here.
Yeah, thank you. Yeah. So, I mean, JWST, there's the images that are being sent back right now are just incredible. And I see new headlines all the time and just the color and all that. We've got the Roman Space Telescope that's being developed right now by NASA. We've got people talking about commercial space stations and putting those up as well as government ones. In terms of, landing on the moon, it's not just Russia, China, and the US anymore, but we've got other nations that are looking at landing in the moon in the next year or so. Japan, South Korea, India, United Arab Emirates. And of course, the moon is kind of a gateway or a port of call for that deep space exploration that James Webb is doing right now, because it can be refueling and kind of resetting, that type of thing. Now, there's lots of arguments about, are these partnerships, or are we in a big space race, part two competition? We need to work out how defense space assets can protect commercial and national interests in these places. And then underlining it all, safety, resource extraction, general entanglement, and then the pure science of it, like what you're talking about, Dave. So I'm going to ask this first question. Whoever picks it up first gets the baton. How can we define deep space? How is it different than other types of space? Don't be shy.
Kenny, you want to go with that one?
That's a good question. I was thinking about my answer to it. When it comes to really deep, because the concept of deep space in general is so relative. Like when you think about how large the Milky Way is, well, not even the Milky Way, when you think of how large the universe is, it's what, 90 billion light years or something like that across. And so it's you think of deep. Does deep mean the Milky Way being that initial that collection of 40 billion stars within your own quote unquote backyard? Even 40 billion stars is huge. Like, so when we think deep, we're thinking outside of our own solar system. That's the first thing that comes to mind. And it's really pushing the envelope to go places that we have not gone before. So the initial thing that came to my mind was, what is the concept of deep? What do we mean by that? But to me, and I think to most scientists and engineers, it means beyond our galaxy, beyond our solar system, into further reaches of the Milky Way galaxy.
Yeah. So it's definitely beyond Earth's orbit. It's beyond that kind of lunar, cislunar thing. Is it anything? I mean, could we count it anything beyond the moon? Dave, what do you think?
I was actually going to jump in because, from the defense side of it, generally I think of deep space as anything beyond geosynchronous orbit, which is still microscopic, compared to the scale that Kenny just laid out for us, 90 billion light years across the entire universe. But I get excited when I think about, the deeper that we can go, the more we can find out. That's what kind of gets me excited. That's why I'm so excited about the JWST and some of the things that we're starting to see.
Let's go with that then. What are you most excited about in terms of the future of space exploration, Dave? And then on the other side of that, what are you a bit cautious about?
Well, I'm most excited about being surprised. I think that whenever we have put a new sensor in orbit, whenever we've looked outward, whenever we've sent a spacecraft to another planet, either to the moon or one of the other planets in the solar system or to the moons, we have always found something that we did not expect. Think about the geysers, coming out of Europa. Nobody knew about that before a particular image happened to capture that. It's the surprise, it's finding out something that we didn't know before. Yeah, it's good to confirm theories, and a lot of what James Webb and what the Roman telescope are going to do, they're going to look at some of Einstein's stuff and keep reconfirming that. But it's even more exciting when we discover a fact that calls into question the theories that we have and makes us think about what's really going on in the universe. Because I still think we don't really know. There's so much stuff that we haven't figured out yet. And that's what excites me about it. I guess maybe there's a cautionary note there too, right? We don't know what's out there. Is there something out there? Be
careful what we wish for.
Yeah, a little bit of that. But I think it's great to find out and know new stuff.
How about you, Kenneth?
Yeah, I want to piggyback off that a little bit. And like I said a few moments ago, it's obviously we know that the universe is huge. So when you think about the Milky Way and those 400 billion stars that I mentioned earlier, we know as of research that has been done so far, that out of those 400 billion stars within the Milky Way, there are about 20 billion sun-like stars. And within those 20 billion sun-like stars, around them, at least a fifth of them have Earth-like stars near them, or habitable planets. If we put that in perspective and just take 0.1% of those fifth, you come up with 1 million planets that should have living organisms on them within the Milky Way. Mm-hmm. So are either of you familiar with the Fermi paradox?
Explain it to us.
I am not.
So the Fermi paradox is this: the Milky Way is approximately 13 billion years old. 13 billion years old, but at the beginning of the formation of it, it wasn't a good environment for habitable planets to form because stuff exploded all the time. So it took about 1 to 2 billion years for the first habitable planet to be formed. We know that the Earth is 4 billion years old. That leaves about 7 to 8 billion years between when the Earth was formed and the Milky Way was formed, that another habitable planet within the Milky Way could form. So the question is, where are the other living organisms that develop within that 7 to 8 billion years? And the scary question is the complex soup that made living organisms here on Earth, or is the event that triggered the birth of living organisms on Earth, was it so unique and was it so rare that we are the only living organisms in that 400 billion stars that make up the Milky Way in general? And so that's kind of it's one of those big questions where you're like, I don't really want to. I don't know if I want to know. so sorry to throw a bunch of numbers out there, but that kind of puts it in context for just how big this question is.
I mean, and this is something that I've been recently intrigued by too, this astrosociology. It's a relatively new interdisciplinary field. And the idea that space can make people question their place, right? Whether their place in their community, their place on the globe, their place in the universe, their spirituality, things like that. I think it's fascinating. So some people are intrigued, some people are scared. Anything to add, Dave?
Yeah, I guess that could go to that little bit of the cautionary note. But, I was thinking about, and now that you remind me, I have heard of the Fermi paradox, which is just, where's the other intelligent life? How come they haven't come in contact with us? Well, maybe they've got, whatever the equivalent is of caution signs, right, around our solar system. Don't let these people know that we're here because they're not ready for it yet.
They're not ready.
It even goes a step further to that, where the paradox includes these things called the great filters. And it's either that the filters are in front of us or the filters are behind us. Now, if they are behind us, that means that living organisms on Earth have overcome these obstacles that would have wiped out other civilizations, and we are advanced in our general thinking of it. If it is before us, then that's bad because that means we are encroaching on the end of living organisms on Earth, and that's again within the framework of the paradox. And again, another cautionary thing where it's we're using James Webb, we're using Roman, and we're using Hubble and things like that to explore the universe and ask and answer these big questions that all point back to are we alone? How rare was it that living organisms came about on the Earth? And what are our origins? I think that's always the biggest thing that anyone is trying to figure out in these big projects or even small projects.
Yeah.
Put out there.
I just think about this. This goes back to why I'm so excited about these telescopes and being able to learn more about what's really out there. There's two ways that you can approach a challenge like this. The Fermi paradox. You can either, and I hate to persecute ostriches, but there's the cliche about the ostrich sticking their head in the sand and hoping the predator doesn't, they don't see the predator because it must not be there, right? Or there's the let's look out and let's find out what's really going on here, because I am convinced that there's way more going on. And I don't know whether it's intelligent life or just other processes that we just haven't learned about. But I am convinced there's way more going on in the universe than we have any clue about right now. And the way we're going to find out is with these great telescopes, these instruments.
So going to that, oh, sorry, go ahead, Kenny. You have something?
No, I was going to say one last thing. And again, putting that into perspective of saying, hey, we have only really scratched the surface of these things, again, just to bombard you with numbers. Again, Earth is 4 billion years old. We know that living organisms took place about have been around for about 3.6 billion years or so, but intelligent human life has only been around for 250,000 years. And of those 250,000 years, we've only had the technology to get into our orbit or low orbit or to the moon or even send communication within the last century. So we've got about 100 years, 100 years we've been doing stuff. And that's just like, oh, we're just scratching the surface. And really, what we're doing here in the present is setting up for future generations to be able to go even further. And I think that's an amazing thought to say that, we're on the front end of answering, again, these really, really big questions.
Yeah, talk about feeling like a little grain of sand on a big beach, huh? Okay, so let's move into some of the more the technology things. So because we could sit here and just suppose about these things forever, right? Because I'm sure a lot of people do, as the practice of astrosociology dictates. But what about some of the cool technological advances being made in some of these deep space programs? And I'll start with you, Dave. I mean, the things I think of like solar sails, nuclear propulsion, space suits, technology. So what kinds of things are you kind of seeing in terms of the cool technological advances?
Wow, there's such a long list of things. I actually am going to start out with artificial intelligence and robotics, because I think that the advances that are being made there are going to be so helpful to us in trying to unravel the mysteries that are out there. If you think about just the sheer volume of space that an instrument like the James Webb Telescope can look at, and of course it's a very thin, basically thin field of view looking at a particular deep area. The Roman telescope is going to have a much larger field of view, although it's still small compared to the entire 4 pi steradians of what you're looking at, when you look out from our little tiny speck here. But I think AI is going to help us a lot in trying to be able to sift through images, find out, astronomers write computer programs are going to use artificial intelligence to help them understand the data. And then I think on the exploration side, robotics, think about what we're already doing on the surface of Mars with the rovers. Think about what we will soon be doing in the Artemis program with rovers on the moon. Chinese are already doing it. What are we going to be able to find out with those robots as they get more and more sophisticated? And then later, as they are there side by side with astronauts, being able to work together to be even more effective. I think it's just a very exciting future, both in looking way out with our telescopes, with our robotic probes going out, but also with what's now starting to be a little bit of a wave of astronauts returning to some of these places. It's just incredibly exciting. Lots of technology options.
Yeah, thanks. And then so Kenneth, Dave, I want to go back to what you talked about with the robotics and stuff, but let me ask Kenneth first, what about some cool technology that you're seeing come out of these deep space? And then, I think when we were kind of prepping for this show, you had talked about, when technology or engineering can go wrong. Like, do you have a little anecdote you want to share?
Well, I don't want to speak about the past, but luckily, again, James Webb has overcome these hurdles of its, 300 single point failures that could have possibly gone wrong while on orbit. But, again, I don't need to knock on wood anymore because we're good. It's deployed. It's given us some great images. But I think that in terms of technology of the future, when it comes to James Webb, it's a testament to how technology continues to develop. It's obviously based around the kind of the same map as Hubble, which everyone is familiar with. And then you took Hubble and you say, okay, well, we want to put the instrumentation on it to up its ability to observe different infrared lights or different wavelengths of infrared lights, but we're going to give it 2 times the view power of a Hubble. And then you take the Roman space telescope, you say, okay, well, we're going to take Roman and we're going to give that 200 times the field of view of Hubble. But in terms of the infrared light that it's observing, it's less than that of James Webb. So this is an example of how we are using 2 different projects in kind of like a tag team sort of format to, again, that ultimate question of our origin, where we come from, the origin of the universe, and ultimately deep space and space exploration in general.
I think that's really cool because when we look at the James Webb images, especially when you compare them with the Hubble images, and you can see all of those extra wavelengths and how they enhance what we can see and the features that start to spring out, just the level of detail. It's really interesting to sort of see how that multi-wavelength technology just makes everything better. The more stuff we can see and more wavelengths, the more we find out.
And there's this really cool image, which a lot of folks are familiar with, the Pillars of Creation. And there's one that is from the Hubble Space Telescope, and then there's the same image taking the same snapshot, observing that same section of space from the James Webb Space Telescope. And you can see just hundreds and thousands of additional stars. They were always there, but what you're seeing is it in a different wavelength of infrared. So instead of near infrared, it's close to mid or far infrared from the James Webb Space Telescope. That allows you to see through dust clouds and all types of other stuff, overcoming that phenomenon in the galaxy of cosmological redshift, just meaning as you move further from the origin of the light, it shifts more along the wavelength. But like you said, Dave, it's really a testament to how far technology has come. And you can, again, I think those side-by-side images are some of the best parts of, being on the James Webb Space Telescope program, that they started off with a glimpse in the past and now a glimpse at how far we've come over the past few decades.
Right. Yeah. Thank you. So I want to go back to what Dave was just mentioning. You talked about artificial intelligence, robotics, in terms of the technological advances. So Kenneth, I'll start with you. What about these robotics in space? the difference between a crewed mission with humans on board and an uncrewed mission. I mean, there's got to be some differences, right? That are pretty obvious. Safety, the need for resources. I mean, do we even need people on missions? Can we just use robots?
I don't know. I don't know if I'm gonna go on record and say we don't need people on missions, but I think in terms of the differences between, and we can kind of get into that differences between crewed and uncrewed missions, but these are my kind of top 5 things that I think are necessary for a crewed mission. So obviously you need life support in some way so that people can breathe and function while on orbit, because humans are squishy in nature, as Dave would say. We need a way to also deter heat, like overheating an environment, or even over kind of stimulating that environment, and also radiation. So heat and radiation, life support, navigation and communication, not only for the psyche of those individuals that are on board, but also so that we can get that data, the whole purpose that they are going out there. And lastly is the ability to move with propulsion. So you obviously need a way to traverse space, and you don't have finite resource when it comes to propulsion. So you will need to be able to move around with that as well. So those are some of the systems that I think are found on crewed missions, and some of those might go away as opposed to using AI technology. And I think Dave can probably speak a little to that. So Dave, what are your thoughts on that?
Well, I was going to just sort of short tail on what you said. I think that if you consider the complexity of a crewed mission versus an uncrewed mission, there's an order of magnitude more complexity and a lot more mass when you need to put together a crewed spacecraft. Let's say we were going to the moon or further on to Mars. And time is the other factor that matters. I can't take credit for the squishy payload. That actually comes from one of our other scholars, Dr. Angie Buckley. She talks about being able to protect the squishy payload with the work that she does with NASA. But the time also matters, because if you're going to put astronauts in that high radiation environment, the less time that you can have them in that environment, the better. And of course, you want to be able to shield them as best you can. And again, that takes mass to do that. But on the other side of the equation, there are still many, many things that the astronaut on the spot can do that the robot or even the very sophisticated AI that's helping cannot. I think I read a quote about the first, it was either the Curiosity rover or it might have even been Curiosity on Mars, where the program director said, yeah, if we had somebody there, they could do things that take us an entire an entire Martian day to figure out, at least right now. The thing to remember, of course, is that AI technology and robotics, they're continuing to get better and better. Our squishy payloads, we are still the same, unless we're going to modify evolution or do something, bizarre, implant electronics or something like that. But we are still staying the same, but the robots and the AI are getting better and better. I think the optimal way to think about this is, what can we do with both of these capabilities together? And I think there are going to be situations where a crewed mission is the best way to go, just because of how much more you can do with that combination of our brains and our cognitive ability combined with the help that we can get from an AI system or from a robot. That combination is really the most powerful at all. But we have to be willing to pay the price in terms of mass and energy in order to support that greater complexity. And Kenny, I know you're a crack systems engineer, so when I talk about the complexity of the crewed mission versus the uncrewed, you know exactly what I'm talking about there.
Yeah, and to speak a little to that, I know one of the biggest proponents of mass and what goes into these missions is the fuel that it takes, not only to get you there, but to also get you back. And I think I don't want to be misquoted, but I think it's Starship. I think SpaceX Starship was experimenting or thinking through the process of utilizing methane on Mars, or harvesting methane from Mars as the source to get us back. So the beauty with that would basically mean that when you're here on Earth, the amount of fuel that you need is more or less cut in half, because you only need the fuel to get to the surface of Mars. Because when you get to Mars, then you can refuel and come back. And that cost savings of that mass is huge, specifically when it comes to crewed missions. I mean, with the AI mission, it can also be better for, additional equipment, more sophisticated technology, things like that. But when you think of mass on a mission that's sending a crew to another planet or into another orbit or just deep space in general, one of the most critical things is not only how we get there, but how we get our crew back, because every mission we've sent has the intent of bringing that crew back, at least to present day. So I think, like you said, but talking to the AI point, I think that they are constantly and continuously getting better over time. And it goes back to that first question that we have. Is it that we want it to get to that? Is that kind of a cautionary thing where we want the technologies to get to that point where it is doing what we can do in a soul? Is that complexity something that we are actively pursuing? I think the answer is yes, but obviously very, very cautionary when you are doing it.
And if we can, one of the exciting things about the Artemis program is the thought that if we get to the moon, being able to lift and depart from the lunar gravity well is far less onerous than trying to leave from the Earth's gravity well. And in fact, if we could even get, some of the volatiles that we need for rocket fuel from an asteroid, at some point in the future, that's an even smaller gravity well. You think about where you might be able to harvest the resources that you need in order to provide that propulsion. And of course, some of the things, I think, Colleen, you mentioned nuclear thermal propulsion. It's a big improvement. A lot of people hype it where it's going to be this huge improvement. It is definitely an improvement and allows us to get to destinations faster. And that's really the key. If we want to go ourselves, we want to make sure that we can limit the amount of danger, the radiation that we're potentially exposed to, or heaven help us if there's a coronal mass ejection that happens to hit us while we're in transit to Mars. That could be a catastrophic event with even 100 times more radiation danger for the astronauts. So being able to protect them is critical, and also being able to maintain their health as they go. Right, we know on the space station that astronauts over a long period of time, they have difficulty. Their bone mass decreases. Their eyesight starts to have difficulty. There might be things that we could do, for example, with artificial gravity on a trip to Mars, where we generate it through centrifugal force that might actually allow us to counteract some of those issues. Going back to 2001, A Space Odyssey, right, with the Discovery spacecraft that spun as it went. That's a simple idea, hard to execute from an engineering standpoint, but definitely something which would allow us to protect the squishy payloads better.
Well, they're working on this. Yeah, they're working on the technology. I can't remember. There's an orbital hotel that's being developed right now. I can't remember the name of the company, but that's just one thing, right?
Or are they going to do artificial gravity? I hadn't read about that. That's exciting. That's a great idea.
And so, talking about I'm glad you touched on the importance, Kenneth, of what David said about mass. So, why is mass, you're sacrificing mass, but why is that a bad thing, right? And it's a lot about fuel and getting off the Earth's surface, and then, introducing ideas of instead leaving from a lunar surface, using different kinds of technologies, the in situ kind of resourcing, if you get to Mars and you extract your fuel to get back, all of that stuff is being worked on from all kinds of different angles. And so are there any other things right now that you can think of that are kind of hard about engineering for deep space? We talked about crewed versus uncrewed, but anything else that you want to pull out in terms of, radiation, kind of having that radiation hard equipment for going further?
I think Dave spoke to it a little bit. I think one of the most difficult things about thinking through these crewed missions specifically is the safety element to them. And obviously mission number one, above discovery and above figuring out again our origins and where we come from, is bringing back our astronauts back home. And it's different than doing an AI approach to it, because you lose money, you lose time, but those are assets that can be replaced. When it comes to the lives of these astronauts, specifically, you talk to people at Johnson and they take it very, very personal when it comes to the safety of them, because these people go to their church, they have kids in school together, they see them at the grocery store, like they're just folks that live amongst us. And so I think the biggest thing is safety. And that's something that's constantly being thought through now. And the concept I brought up about mass not only relates to fuel, but I think if you were writing an equation out for the projects that you're working on, I think that the mass is very, very precious when it comes to sending stuff to space. And I think that is directly correlated to how far we can go, the life expectancy of the mission, how much we can possibly accomplish. So I say all that to say that we have to figure out the sweet spot of what is viable trade-offs between the technological route with AI and robots and the crude route with humans. And like Dave said, to specifically speak to how space affects them, again, not only physically, but also mentally. So it all circled back to that aspect of safety is what I was getting to.
Dave, anything to add?
You know, we talk about how daunting the challenge is, but I have great faith and optimism in the ability of these squishy payloads, all of us, the world, to be able to figure out how to solve these problems. I mean, if you just look at how the cost of launch has decreased just over the last 10, 15 years. And I know Elon and Bezos and others are trying to decrease it by even another order of magnitude in terms of cost. And if you think about clever strategies that we could use in order to get our fuel elsewhere, there are definitely ways that we can solve the mass problem and be able to send both robots and people out into at least our solar system, and I hope eventually to other stars, although that's a whole nother leap. I think the order of magnitude, you know, going from the distance from here to Jupiter versus the distance from here to Alpha Centauri, it's like a factor of 40 or 50,000 in terms of the distance.
Right.
And of course, that all goes back to time and what kind of propulsion system you have and how long the squishy payloads survive. Robots, however, you know, they can last a long time. So I think there's just incredible promise in the combination of the technologies, and we should just keep pushing on all fronts. All of it is exciting and inspiring to us.
And so going on that, you know, you talked about how us humans, I'm sure we can solve the problem. So, you know, let's talk about solving problems. Let's go into a little bit of policy, since this is a state policy show and policy is about problems, right? So how do priorities in space, how do they get shaped by policy? I know, Kenneth, you had talked about the decadal surveys. And so maybe you want to tell the audience a little bit about that and anything else that comes to mind, and then I'll go to Dave.
Yeah, so that's specifically what I was speaking to was specifically for the James Webb Space Telescope, and that decadal survey comes from the Astronomy and Astrophysics Advisory Committee. Specifically, it's more or less the ask of what we are looking to find. I mean, it's a survey, but it's asking what are we looking to find, what are we hoping to accomplish, and then bringing in the necessary technologies to accomplish that objective. Now, it's made up of several different organizations, and it's kind of a collaborative effort of starting with this really big project idea and boiling it down to a space telescope with 300 single points of failure and 4 instruments on it. And from that survey is how it was boiled down to the James Webb Space Telescope. I think Roman's included in that as well. And that's again, that's a collaborative effort. And that's one of the ways that we, outside of like the politics and outside of the changing waves of administrations and things like that, that is another way of how we decide what projects are coming down the pipeline in future decades.
Yeah, you want to add to that, Dave? And even, I mean, I'm thinking even certain international agreements too. But what else, Dave?
The thought that struck me was we were talking about solving the technical problems earlier, right? That's the easy part. Solving the policy challenges, you know, getting international partners to work together, figuring out the work share, making sure that everybody is respected and that everybody can contribute. That's often where some of the real challenges lie. And yet we're stronger by working with international partners and with commercial partners. Think about what's happened in just the last 15 years in terms of private equity, private individuals getting involved in space exploration, and the kind of a difference and impact that has had. I think that, as I said earlier, pushing on all fronts, partnering with international partners, I may be I am a cockeyed optimist, but, I hope that someday, we'll be able to work with the Chinese and do incredible things together. I don't know if that's going to be possible. It certainly doesn't seem possible right now. But we're managing to work with the Russians right now on the International Space Station, pretty much because we have to, despite the fact that there's hostilities going on elsewhere. But those international policy issues are challenging. Sorry, go ahead.
Yeah, no, I was just going to say, certainly if the US does not work with China, there's I'm sure there will be other countries that step in for that partnership. And so that's something to keep in mind.
And there are, if I can piggyback off, there's a lot of other organizations. I don't want to call them smaller, but new up and coming kind of space agencies and things like that. We know the bigger ones on the planet are NASA, JAXA, which is Japan, ESA, the Chinese Space Agency, and Russia. But there are other ones that are, again, up and coming. There's the Space Agency Development in Africa. Australia has a space agency, and they're doing some of the most amazing kind of cutting edge work when it comes to developing lunar rovers. Like they had this big project they were doing with lunar rovers. There's also the Polish Space Agency, and there is a conglomerate of individuals that have kind of come together under these different organizations to, again, kind of say, hey, space is for everyone. It's not owned by anyone. We have that objective of getting out there and discovering new things and seeing what the universe has to offer Earth. And it's those individuals that I think are going to help propel us into the future. And we didn't talk about this, but one of the bigger ones or bigger problems that the world as a whole and these collective agencies need to figure out is space debris. And that is a huge thought, huge kind of project where, everyone wants to get to space, but no one wants to accept the responsibility of space debris. And so my kind of thoughts about it are, are there going to be policies? There's going to be a lot of conversation around how we handle space debris. But that's just kind of a nod to our international collaboration that we're having with these different groups.
Yeah, I mean, and it's an all in. We're all in the game right now. We've all got skin in the game. So I mean, the idea that that governments are creating these national space agencies or offices. I mean, the business ventures of commercial space cross national boundaries. So just because you pass a rule or a law in the US doesn't mean it's going to be universal. So yeah.
No, I strongly support what Kenny is saying about getting everybody in the world involved. And there are lots of new innovative ideas coming out of places where you at least expect them. And that is a really wonderful thing. Technologies coming from Latin America, from Africa, from other places around the world. And the more that we can make in an international effort, and when we find out stuff about what's really going on in the universe, broadly share that. I know there's these astrosociological concerns, right, about what we might find out and how that might affect us. But I think that people are pretty adaptable. And we're pretty open to change, and we can adapt to new circumstances, and we can solve these problems. So I'm still optimistic for the future. Until proven otherwise, I'm going to be optimistic. And it's better to find out. It's better to have our ostrich head up and looking around rather than down in the ground.
Kenny, how about you? Any final thoughts?
I had a question for Dave, and it's funny enough because I was speaking to a group of middle schoolers, and this question came from them. It's not the first time I've heard it, but it came from them in terms of, what are your thoughts and what were my thoughts on the justification for utilizing funds to continue space exploration as opposed to dealing with, problems that are here on our planet. And how do you typically answer that question, Dave? And then I'll follow up. Anyway, Colleen?
The way that I think about that, Kenny, is I always go back and I often ask people a question in reverse. I say, how much money do you think that we're really spending on space exploration? How much of the federal budget do you think we're spending, right? And oftentimes I'll get an answer like, oh, we spend 20% of the federal budget. That's what NASA is. And that just blows my mind because the actual number is like less than half of 1%. And the amount of money that we spend on space is really small. So I guess what I'm really saying in answer to your question is we have a responsibility to do both. We don't want to ignore the needs that are out there, and we need to do what we can to address them. But I also believe that space is part of the answer. You think about the work that space sensors do relative to monitoring the climate and understanding climate change, monitoring our closest star, right, the sun, telling us what's going on there. That could have a big impact on our climate, and understanding any changes there are pretty important. And then there are all of the secondary and tertiary effects that come from advancing technology in any area, space included, right? When we're pushing the boundaries, when we're learning new things, we find out stuff that filters back and allows us to help everyone in terms of improving technology. Just think about the fact that we have the internet. Think about the fact that we now have smartphones and the computer technology that came from that. Those didn't all come from space, but space was certainly a driver for improving computer technology. And every place where we push technology, whether it's in space, whether it's in the biosciences, whether it's in figuring out how to produce better computers, how to do better communications, how to build better roads, how to, anything that we do where we're advancing science, that's going to come back and have benefits in terms of innovation, things that will help everybody's standard of living improve all over the world. So I think we have to do both, but we also have to think about how incredibly uplifting looking out is and how that lifts all of us and helps us realize where we really are in the universe. I just think it's a very important thing not to be neglected. That was a ramble, by the way.
No, all good stuff. I think that's spot on. I think it's incredible what we as an industry have done, again, with that very minute portion of these funds that are received. And I gotta say, I use the word minute loosely, but in terms of the entire, budget. And I think, again, it's really important, not only for explorative things in nature, but to help us understand kind of the direction Earth or humans might be going in. And going back full circle to that Fermi paradox that we talked about at the beginning, hypothetically, if we think about if, again, that soup that created humans or that trigger or that catalyst is so rare that we are the only ones in either the Milky Way or, this corner of the universe, I think that it is imperative that we continue to explore and continue to expand and continue to, again, push that boundary of science in some way while also caring for our own home planet. So I think there's a good balance to it. I think there's some things that can be moved, but I think it's a good balance. I'm gonna go ahead. I see your head.
No, I was just thinking, I want to jump on what you said again, because it makes me so excited. The JWST and the Roman telescope, they have specific instruments. The Roman telescope has one of the most advanced coronagraphs that will allow us to block the light of the star and really focus in on the nearby planets. And the James Webb telescope has that spectrograph that allows us to look at the spectrum of what's in the atmospheres of some of these exoplanets. That's going to tell us some of this stuff about whether or not life can be there. It's going to be mind-blowing. And so once again, they're providing us with the tools that will help us answer exactly the question that you're talking about, the Fermi paradox. I think it'll help us find out.
100%. I think, again, in addition to those really cool images that have come out from the James Webb Space Telescope, like you said, we've utilized that spectrograph on board to take images collect information from WST 96b, I think that's what it's called. And they have a graph that shows the atmospheric characterization. You can see water molecules and things like that we have sensed from a single pass of James Webb. And I think that's amazing because, before last December when this thing launched, we didn't have readings that were this in-depth. And that, again, speaks to the future of technology and the future of what we can continue to do if we do pour money into these spaces and we continue to explore at a very controlled and very thoughtful pace.
Yeah,
thank you for answering the question. I know that was left field.
Yeah, I mean, when I'm being cheeky, I just answer that question as well. We need a plan B because we're not doing too good on this planet. But yeah,
there is that.
Yeah. Well, the value you mentioned, Dave, the value that space brings to life on Earth in terms of, maximizing, crop yield for agriculture, minimizing the use of pesticides from, sensing satellites.
Helping us find our way around.
Yeah, I mean, communications are, everyone knows that and that's in their back pocket, but I'm just fascinated by the things that we don't know space provides us. That people don't realize that every day we're actually improving life on Earth using space assets. So, and then the entanglement. Huh?
And Colleen, I think it's another thing you mentioned, some things that people just might not know about. I think when people think space programs, they automatically think, oh, James Webb, it's $1 billion project. Why do we spend or waste $1 billion on a telescope? When you think about that pocket of money we have, it's not solely for, again, observation-based, external-looking projects. There are a number of satellites, there are a number of projects that look internal to the planet. So you think of, again, communications, you can think of JPSX or even the GPM programs, which projects are international projects, where they're helping to track natural disasters. So hurricane and tornado monitoring, wildfire monitoring, animal migration, so we can understand animals on the planet, agriculture, and things like that. Those programs give us bird's eye views of not only helping to protect individuals, but helping us to better utilize resources that we have on the planet. So I think that's a full circle to some folks not knowing that there are internally looking programs that help our planet a lot.
Yeah, I mean, tracking illegal fishing, human trafficking. I mean, these are all things. Yeah. So that's I'm enthralled by that, and then just the general entanglement, how space things cross national borders, and just the whole meatball effect. That NASA meatball of what we're looking down on is borderless. So, yeah. You guys, thank you very much for joining today. We totally went over time, but that's okay. It's the last show of the year. And I want to thank both Dave and Kenneth for joining us today.
Thanks.
Thank you so much for having me and having us, Dave. It's been wonderful talking to you. Anytime you want to have fireside chat, we can get on and nerd out anytime with me, man.
I look forward to it. We should do it. Thanks, Colleen.
Okay, so viewers, listeners, thank you for joining us this entire season. We'll be back in January, but in the meantime, please subscribe to our newsletter. You can follow us on our YouTube channel or any podcast platform, and then you don't miss anything when we do start back up again. You'll get instant notifications. If you missed any of today's show, all of the shows are available to watch or listen to the day after they're released. So just go to the events webpage at csps.aerospace.org. James Liggins is our technical director. He's going to be taking a very well-deserved break over our hiatus. So thank you, James, for all the great work that you do. And thanks for watching Aerospace Corporation's Space Policy Show.